The data came down from a JWST during a routine calibration run, and the researchers who first looked at it knew immediately something didn't fit. Not broken. Wrong in a different sense. The universe was not supposed to look like this yet. XLSSC 122, a galaxy cluster sitting roughly 10.2 billion light-years away in a stretch of cosmic history where clusters are still supposed to be under construction. This one is finished. Its galaxies are old. Its hot gas is already enriched with heavy elements. Its stars stopped forming long before the light we're seeing left them. The press releases called it a milestone. The papers, read carefully, called it something closer to a warning. And the gap between those two descriptions is worth sitting with, because it's the entire story. Here's what you need to hold in your head before anything else makes sense. XLSSC 122 sits at Redshift 1.98, first flagged in the mid-2000s by the XMM Newton X-ray telescope as part of a large-scale structure survey, an extended faint source too bright at that distance for a young, still-assembling cluster. Follow-up work over the following decade sharpened the concern rather than resolving it. Then, in 2020, astronomer John Willis and his team confirmed the redshift spectroscopically using the Hubble Space Telescope, identifying 37 spectroscopically confirmed member galaxies. That redshift translates to a light travel time of about 10.2 to 10.5 billion years, meaning we're seeing this cluster as it existed when the universe was only around 3.3 billion years old. Here's the part that should stop you. Willis's team found that star formation in this cluster's oldest members began when the universe was just 370 million years old. Not a billion. Not a billion and a half. 370 million. And by the time the light we're now receiving left the cluster, that star formation had already finished, aged, and shut down. Read that again. A fully mature, chemically a cosmic moment the Standard Model says should still be laying foundations, not retiring them. This is the tension. Not a hoax, not a broken telescope, not a conspiracy. A real, published, peer-reviewed strain between what JWST is measuring and what the leading cosmological model, Lambda CDM, predicted should exist at that point in cosmic time. Here's the story most people have heard about JWST. It's the most powerful space telescope ever built. It launched, it worked, it sees farther than Hubble, and it keeps confirming how impressive the universe is. XLSSC at 122 fits neatly into that story as a distance record, a striking image, proof the instrument works. That version isn't false, it's just softened. Read the actual abstracts and the language shifts. Words like unexpected, mature, quenched, intention with. These aren't celebration words. They're pressure words, the vocabulary researchers reach for when data isn't behaving the way a model said it would. So how does a cluster like this actually get built? And why is finishing this early a genuine problem? Galaxy clusters are the largest gravitationally bound structures in the universe. In the Standard Model, they're supposed to be the last major structures to finish assembling, not the first. Dark matter collapses into halos. Gas falls in, cools, and forms early galaxies. Those galaxies drift toward each other over billions of years, merge and pile into groups. Groups merge into clusters. Only once enough mass is accumulated does the surrounding gas heat to the temperatures that make a cluster detectable in X-rays at all. It's a sequence. You don't skip steps. You don't get a finished skyline before the roads get built. Entirely. It's cold gas, either exhausted, stripped away, or heated past the point where new stars can condense out of it. The galaxy is still there, still visible, just drifting through the rest of cosmic history as an aging, red, closed system rather than an active one. Researchers studying XLSSC 122, including a 2021 follow-up by Eric Nordy and colleagues, found that roughly 88% of galaxies within the cluster's core are quenched, confirmed through spectral features like the 4,000 angstrom break, a fingerprint that only appears once a galaxy's stellar population has had real time to age. That fingerprint shouldn't be this strong in this many galaxies at once, this early. A 2024 JWST-based imaging study using strong gravitational lensing to sharpen the view of the cluster's densely concentrated core confirmed the same picture in even finer detail, statistically flagging XLSSC 122 as an improbable detection, the kind of object models suggest should barely exist at all across an entire survey field this size. Quenching requires a mechanism, supermassive black hole feedback heating surrounding gas, ram pressure stripping as galaxies move through a dense cluster environment, strangulation as the supply of fresh gas gets cut off entirely. Every one of these processes takes real time, and every one requires a level of environmental maturity that, in the standard timeline, this cluster simply shouldn't have had access to yet. Either these mechanisms ran faster than anyone thought possible, or something is missing from the model. And here's the detail that matters more than any single cluster on its own. XLSSC 122 isn't alone. Since JWST began science operations in 2022, it has repeatedly flagged early universe objects that appear too massive, too developed, or too chemically advanced for their place on the cosmic timeline. Surveys have turned up galaxies at extreme redshifts with inferred masses that would require an implausibly large fraction of all available ordinary matter, at that epoch to already be locked into stars. Separately, JWST has found supermassive black holes that reached hundreds of millions of solar masses when the universe was under 1 billion years old, growth rates that sit uncomfortably close to the physical limits current. Models allow, forcing theorists to consider exotic seeding mechanisms nobody needed to seriously entertain before this telescope launched. Now add a fully assembled, chemically enriched, quenched cluster to that list. 3 different categories of object, 3 independent lines of evidence, discovered by different teams using different instruments and different techniques, all pointing in the same direction. The early universe built structure faster than the standard model expected it to. One anomaly is a curiosity. A pattern across independent object classes is something else. It's worth being honest about scale here because cosmological models don't absorb tension evenly. Each new anomaly adds pressure to the same underlying parameters, and there's a point where outliers stop being explained away as outliers and start functioning as data the model has to actually account for. Hubble had its own surprises in the 1990s, more distant galaxies than expected, showing up in deep field images, and the field absorbed those by refining. This isn't the first time cosmology has faced pressure like this from multiple independent directions at once. In the late 1990s, persistent tension between supernova brightness measurements and the expected expansion rate eventually forced the introduction of an entirely new component of the universe, dark energy. Nobody predicted it cleanly beforehand. The data essentially demanded it. Measured by the Planck satellite, one based on supernovae and other local distance markers, produced 2 different numbers. That disagreement hasn't shrunk as measurements improved. It's held, and in places grown more statistically significant. One proposed fix involves something called early dark energy, a component briefly active in the universe's first few 100,000 years that would also change how quickly structure could form afterward, which is exactly the direction JWST's early universe anomalies are pointing. 2 separate problems, measured with completely different techniques, both nudging toward the same possible explanation. That's not proof, but it's not nothing either. Now, why does the public mostly hear the confident version of this story rather than the hedged one sitting in the actual literature? There's a structural reason, and it isn't a conspiracy. Space agencies fund telescopes by demonstrating success, and that success is what keeps future missions funded and careers intact. When JWST delivers an image like this, the institutional instinct is to lead. With the win, the distance, the clarity, the sheer capability of the instrument, all of that is genuinely true. The tension inside the underlying science is also true. But tension doesn't compress into a press release headline as cleanly as a triumph does. In tension with the standard model becomes reveals surprising details, challenges. Current formation timelines offers new insights. Every individual softening is defensible on its own. The cumulative effect is a public that walks away believing cosmology is settled, while plenty of working cosmologists know it currently isn't. Nothing here is hidden. The papers are public, the hedged language sits right in the abstracts, and researchers are actively arguing about exactly this in journals and at conferences. What's happening is a translation gap, not a cover-up. To be clear about what this is not saying, this isn't evidence the Big Bang didn't happen. The cosmic microwave background is real and precisely measured. Light element abundances match nucleosynthesis predictions with extraordinary accuracy. The broad framework holds. What's genuinely under strain are the finer details, exactly how fast structure assembled, exactly when the first heavy elements formed, exactly how early chemistry complex enough to matter for planets and life became possible. And those finer details are precisely where the story of how we got here actually lives. Every downstream date in cosmic history inherits from the early universe formation rate. If clusters like XLSSC 122 were assembling and quenching roughly 2 billion years earlier than expected, the timeline for heavy element enrichment shifts earlier too, and with it, the earliest plausible window for rocky planets and the chemistry that could eventually support life. That doesn't mean anything about extraterrestrial life is confirmed or denied. It means one of the quiet assumptions sitting underneath modern astrobiology, that we exist near the front edge of a universe that only just finished cooking its own ingredients, may need real re-examination. So where does that actually leave things? XLSSC 122 isn't proof that cosmology is broken. It's evidence that a specific piece of it, the pace and mechanics of early structure formation, is genuinely unfinished, and that the gap between the confident public summary and the hedged working literature is wider than most casual coverage lets on. The age of the universe, quoted as 13.8 billion years with striking precision, isn't a direct measurement. It's a fit, derived by combining the cosmic microwave background with a specific model and a specific set of assumptions about how the universe evolved. Change those assumptions, and the fit shifts. That's not a scandal. That's how physics has always worked at its edges, small residual anomalies accumulating from multiple independent directions until they eventually force a real revision, the same pattern that preceded relativity, quantum mechanics, and dark energy. The photograph of XLSSC 122 that came down from JWST is genuinely beautiful. What it shows is a structure that either broke a rule the standard model relied on, or is quietly pointing toward a rule that was incomplete all along. Both readings are serious. Neither one is the version that made the headline. And that gap between the picture the data is actually describing and the picture the summary offers is exactly where the real story is still being written, one paper, one anomaly, one carefully hedged abstract at a time.